In this video, we look at examples of stoichiometry involving aqueous solutions and gases. Recall from the last video that stoichiometry is as easy as 1, 2, 3. Step 1. Get into moles if not already in moles. Step 2. Change substances using the molar ratio from the balanced chemical equation. And step 3. Get out of moles if needed. The molar map can help you identify which conversion factors are needed for steps 1 and 3. At the center of the mole map is the molar ratio. In the last video, we used molar mass to convert between grams and moles. In this video, we are going to use the ideal gas law and molar Here's our first example using solution stoichiometry. How many liters of a 0.115 molar potassium iodide Ki solution are needed to react with 0.104 liters of a 0.225 molar lead-2 nitrate solution? First, we need to recognize that whenever we see a molarity, it is a conversion factor that can be used between liters of solution and moles of solute. We are given two molarities. 0.115 moles of Ki are in 1 liter of the Ki solution. And there are 0.225 moles of the lead-2 nitrate in 1 liter of the lead-2 nitrate solution. We need to begin our calculation with the quantity of that solution that we are given, 0.104 liters of the lead-2 nitrate solution. We will also need to create a molar ratio using the balanced chemical equation between these two substances. 2 moles of Ki react with 1 mole of the lead-2 nitrate. There will be 3 conversion factors for this problem. Our first conversion factor is going to use the molarity of our lead-2 nitrate solution to cancel out liters and get into moles of the lead-2 nitrate. Our second conversion factor is going to cancel out our moles of lead-2 nitrate and get into moles of potassium iodide. Lastly, we are going to cancel out our moles of potassium iodide and get into liters of that potassium iodide solution using the molarity of that solution. As always, copy the unit and the substance label from the numerator of one conversion factor into the denominator of the next conversion factor. After we use our calculator, we find that the required solution volume is 0.407 liters of the potassium iodide solution. Our next example will use a gas at STP. What mass of iron, Fe, will react with 5.5 liters of O2 at STP? The balanced chemical equation is 4Fe plus 3O2 becomes 2Fe2O3. We are asked to find grams of iron, and we are given liters of oxygen gas. We do not need any information about the product Fe2O3, so we can ignore it. Because oxygen is a gas at STP, we use the molar volume of a gas. 1 mole of oxygen at STP will occupy a volume of 22.4 liters. Iron is a solid, so we will use its molar mass. 55.85 grams of iron is equal to 1 mole of iron. From the balanced chemical equation, we know that the molar ratio is 4 moles of iron for every 3 moles of O2. Our calculation is going to have 3 steps. Our first step is to convert from liters of oxygen into moles of oxygen using that molar volume. Next, we need to convert from moles of oxygen to moles of iron using that molar ratio. And lastly, we need to convert from moles of iron into grams of iron using its molar mass. After rounding for 3 significant figures, we find that our answer is 18.3 grams of iron. That is how much iron is required to react with 5.5 liters of oxygen gas at STP. Molar ratios can be applied directly to gas volumes, assuming pressure and temperature are constant, or molar ratios can be applied to gas pressures, assuming that volume and temperature are constant. Consider this example. N2H4 decomposes into N2 and H2 gas. If this reaction occurs in a closed container at constant temperature, what happens to the pressure after the reaction goes to completion? Is it A, the same as the initial pressure, twice the initial pressure, 3 times the initial pressure, or other? The correct answer is C, 3 times the initial pressure. But why? The problem states that the temperature and the volume of the container remain constant. Under these conditions, the pressure is directly proportional to the number of moles of gas. On the reactant side, there is 1 mole of gas. On the product side, there are 3 moles of gas total, 1 mole of N2 and 2 moles of H2, for a total of 3 moles of gas. Since the number of gas particles triples, the pressure also triples. During the electrolysis of water, 100 milliliters of oxygen gas is collected. What volume of hydrogen gas is produced? The balanced equation is 2H2O liquid produces 2 hydrogen gas plus 1 oxygen gas. The molar ratio is 2 moles of hydrogen gas for every 1 mole of oxygen gas. Under the same pressure and temperature, the gas volumes follow the same ratio as moles. Therefore, 100 milliliters of oxygen gas equates to 200 milliliters of hydrogen gas. If a gas is not at STP, we must use the ideal gas law. Determine the volume of hydrogen gas produced when 1 gram of gallium metal reacts with excess acid at 25 degrees Celsius and 1 atmosphere, according to this equation. Gallium solid plus 2H plus aqueous produces 2 gallium plus aqueous plus H2 gas. We are asked to find the volume of hydrogen gas. We are given 1 gram of gallium, 25 degrees Celsius, and 1 atm. We must first rearrange the ideal gas law to solve for volume. V is equal to nRT over P. To use this equation, we first need to find moles of hydrogen gas. We have to start with 1 gram of gallium to do that. And we will convert from grams of gallium into moles of gallium using its molar mass. 1 mole of gallium has a mass of 69.723 grams. Next, we use the balanced chemical equation. 1 mole of gallium produces 1 mole of hydrogen gas. This gives 0.01434 moles of hydrogen gas. Now substitute into the ideal gas law. I will use an R value of 0.082058 liter atmospheres per mole Kelvin because the pressure I am given had a pressure in atmospheres. My temperature also needs to be in Kelvin. When converted into Kelvin, my temperature is 298.15 Kelvin. Substituting in the values that we are given, and solving for volume gives a volume of 0.350897 liters, which is equivalent to 351 milliliters of hydrogen gas.